Hey everyone, welcome to this new kind of an experimental playlist where every week we are going to take one of the deep learning research papers, deep reinforcement learning research papers to be specific. You will find the GitHub repository to the entire list in the description of this video. And what we are going to dive into in this session is one of the legacy papers or one of those very super cool papers which kind of revolutionized the entire deep reinforcement learning paradigm. So, in this session, we'll be looking into how AI can learn to play video games, not by being programmed with rules, but by figuring things out on its own, just like we humans would do in the real world, right? No one really taught you the rules of Super Mario game or ping pong game or any kind of game as such. So that's what we are going to do in this session too. We are going to break down a very famous paper from DeepMind called Playing Atari with Deep Reinforcement Learning. Don't worry if that sounds complicated. I'll explain everything step by step. So let's get started. What's happening here is let's look at what does this paper propose exactly. What is this paper trying to present in general? What can we see over here is it was one of the first deep learning models to successfully learn control policies. I hope you have basic understanding of reinforcement learning. If not, then just let me know in the comments. I'll try to create an entire different playlist in between so that you understand what reinforcement learning policies are, value functions, Q function estimation, and all those kind of things, because that prerequisite might be very important for this, but you don't need to know everything about deep reinforcement learning or reinforcement learning as such to understand the outcomes of this paper or the possibilities that this paper tried to present. By the way, this paper as of today is like around 14 years old, so it's January 2025. This was in December 2013, which is around 14 years ago. And one of the papers that revolutionized the way deep reinforcement learning is used these days. So, how and what did they do differently than others that it became such a huge thing in that era as well? So, let's see. Basically, what they really use is a very simple convolutional neural network trained with a variant of Q learning. So, Q learning is the key algorithm that they have used, but there are some tricks that these guys used. Basically, the only person that I know from this entire team is David Silver. Unfortunately, I know that all of these guys are amazing researchers globally, but David Silver is one of those pioneers who really taught me reinforcement learning. I saw his video lectures and followed him through, and that's how I learned reinforcement learning myself. So I know about him, but I'm so sorry I do not know a lot of other people. But I'm sure that they are very popular and they're doing pretty well today as well. Anyways, coming into what input are we providing to our system? We are giving raw pixels, and what are we getting in return? We are getting value function estimates of at any particular state. So, whenever we are trying to play a game, for us to perceive any game is kind of simpler because we know that, okay, that one thing is us, we are the character, we are the ones playing the game. If I move left, right, up, down, these kind of steps I do, I'll understand that, okay, these are the things that I'm capable of doing. I put those actions out there and try to mess around with the environment. I might fail sometimes, I might win sometimes, that's totally fine. But what I really learn from doing these very random movements, random experimentations, is that what is the scope of my own movement, and within a couple of games I might just get good at that, good at the entire game as such, all the levels in fact. So the thing about computers is that it's not really that easy for them to understand that, okay, they are the main character, this is how the world will look like if they move up, down, things like that. So The reason that this paper is so revolutionary is because they have used raw pixels instead of some vectors that previous algorithms used earlier. So what they are trying to experiment over are these seven Atari 2600 games. I'm not sure is that the number of games that Atari has or something like that, but basically they are trying to play seven different games, and the outcomes are pretty good. So earlier, before this paper, before 19 December 2013, people used to have a very specific algorithm, a very specific way of learning several games. For example, Mario will have an entirely different algorithm, and let's say Pong will have an entirely different algorithm, Breakout will have an entirely different algorithm. So if you use the same algorithm from Breakout to Mario, it might not work as good. So those exchanges were not really allowed, or were not we were not really capable of doing those exchanges until this paper came out. What this paper brought out to give an outcome as is this one deep queue network algorithm that you train any game on will definitely perform much better than all those legacy models. So yes, not all of them, but this approach proved well for six of the games and surpassed human expert on three of these games. So out of like seven games, this algorithm won against a human in three of them, but lost four out of these. I think that's completely fine. As you know, it's basically an algorithm and still doing pretty well. But I think this was a bigger breakthrough that all the previous algorithms, which are very specific for that game, it could even outperform those existing algorithms. So that's something that I really liked, and I really like this human expert version thing as well. That when I'm playing a game, within a couple of games, I might become an expert too, and I would not want a computer to win against me, right? So let's get into the crux. So these are a few games that we are talking about. Left one is Pong. This is Breakout, Space Invaders, Sequest, Beam Rider. I actually know only about the first three. I have not played the rest, but you get an idea. You can check that out. A few more important things about this paper is the reward function. It's basically giving a discounted return. We'll be talking about these in much detail. They have also mentioned the Q star thing, Q star formula that is essential for value function estimation. And some things that I would like to talk more about is that we are into a completely model free environment in this scenario. What do I mean by model free? And so algorithm does not really know anything about what's happening in this model yet. So it has to experiment. It has to make different movements, up, down, left, right, whatever those movements are for that particular game. It has to, for example, I'll give you an example of what these movements are. So for breakout, there could be three movements. We are able to only control the paddle, right? So we only control the paddle. How can we control the paddle? Paddle can go either left, it can go either right, or it can stay at its own position. So that's what we are trying to control right now. And these are the three action, and this is called as action spaces in our reinforcement learning. So this action space is limited, and we can only play around with it. No one tells you that okay, if the pong or this ball is very farther away, then you have to move in that direction or not in that direction. No one is going to tell you about it. What you are going to know is that okay, there are these left control, right control, and this stop control. You still do not know what do these controls do. You just have to experiment. You just have to keep on experimenting throughout the environment. Move left, right, see how those pixel values are changing on the screen, and that's how model free environments work. That no one tells you that this is something that you have to do, this is something you should do, go that way, go this way. No. So that's also an important think that in real world, it's we are just trying to simulate the real world environment, that we are more of into a model free world. Fine. Okay, so it is also an off policy thing. Off policy actually means that it learns first. Uh, so it first learns an algorithm. Particularly in this one context, what off policy really means is that we are trying to learn the approach where this agent or this pedal learns about a greedy strategy while following a different behavior distribution to explore environment. So you explore something, whenever you do something good, you give that policies that policy to another different policy, that is the greedy policy. So you are now playing between a greedy policy and a behavior policy. Now what is this greedy strategy or greedy policy is it's basically the policy that always chooses the action that is expected to yield the highest reward based on the current estimates of the action values. Now these current estimates of the action values come from that particular state only. The agent learns about the greedy strategy while its actual behavior is dictated by the behavior distribution, which might include a random element. Fine. It's exactly, I'm just exactly reading out what's here just to give you a clear idea of what exactly is a behavior policy and a greedy policy. So here's where they're talking about greedy strategy, and here's where they are talking about the behavior policy or behavior strategy. Behavior policy will have some sort of randomness. Greedy policy will always choose the best particular action given the state, and theta are the function parameters that we have approximated. So don't confuse yourself. It just means that the policy being learned is different from the policy that is used while playing the game. And there's something also known as on policy learning, where the policy being learned is the same as the policy being used to generate experiences, which is a lot easier than off policy as such. But off policy is basically an industry standard as of now. So this paper especially mentions that deep Q learning algorithm is basically an off policy method. It learns about the optimal policy, that is the greedy strategy, by using experiences gathered from different behavior policy, that is the epsilon greedy one, which is needed to explore the environment's entire ecosystem. Fine. The use of experience replay comes later on, which is one of the key findings of this research paper. Let me talk about that now. All right, it took me quite some time to look into this experience replay. I was trying to search throughout the entire paper that where are the places where they have exactly mentioned it, but now as I found it, it's not like deep Q learning is very new or something like that. No, that's not really true. Deep Q learning has existed before this paper as well. However, this paper introduces something called as experience replay, which was never used with deep Q learning before. So introduction of experience replay actually made deep Q learning very much more practical in nature for such applications and for such good quality results, I would say, just to sum things up. Okay, so imagine you are playing a video game and sometimes you do really cool things that help you win, but sometimes you make mistakes. Fine. Experience replay is like having a special kind of memory box, I would say, where you can track all these cool things and mistakes you have done while playing. But every time you do something in the game, like move the character or press a button, you remember what you did, what the game looks like before and after, and if you got any points or not. You look at these things. This is called an experience in technical terms, and it is stored in this kind of memory box. Fine. You are doing something, you are collectively storing that into your experience box, experience or memory box, anything you would like to call. So this memory box can only hold a certain amount of experience. Of course, like, you have got a toy box, you can only fit a certain amount of toys, not more than that. Similar like to that, it only keeps the most recent ones. So as you play the oldest experience, as you play the oldest experiences that you did are removed automatically from that memory box, and new ones are getting added constantly. Then instead of learning only from what you just did right now, you take out a bunch of random experiences from the box while picking a handful of, the way you pick a few toys from the toy box, exactly like that. If you look at these random old experiences and try to learn from them, this helps you learn from all the things you did, not just the last few things, and also help you learn from your mistakes, that you did something good or you did something bad. This way it is like you are learning from a mix of all the different things, that this is good and this is bad, um, that have happened while playing, not just like the last few things. So that's the very important part of this algorithm. The question is, why is this memory box so helpful? It's a very completely random idea, isn't it? That okay, fine, just store everything. So the question is, why not to store every single experience? Why to just why to delete the older ones? Why to keep only the newer ones? Why so these whys are very important, so that we can understand the algorithm better. So first, let's answer, why is this memory box so useful? This memory box lets you learn more. That is, by using this experience, or these experiences from the memory box more than once, you get more chances to learn from them. Like, I hope you get an idea with this toy example, and it helps you learn better. You're not just focusing on the good ways, or only the actions that helped you reach some reward. No, you are not just focusing on them. You're also focusing on mistakes that you should not make, which you were penalized for earlier. This memory box also prevents you from getting stuck somewhere. So there is a huge problem in reinforcement learning called as getting stuck into a suboptimal behavior. This memory box will also help you explore enough of good and bad examples so that you do not get stuck into that suboptimal behavior, or that suboptimal way, or suboptimal policy, we call that in reinforcement learning. So you don't want to get stuck into those things, and that's why it is very important to use this experience replay. By the way, there are a few more things that I would like to discuss regarding this algorithm, and that is this introduction of phi s. This is basically the pre-processing step. Over here, you see these are the games that we are trying to play, and every single one of them is very well colored. And one basic idea that you will get out of it is these games are very pixelated, or have completely distorted pixels, if you understand that. These are very small games, very tiny ones, but that's how that's what makes this thing a little feasible. And that in 2013, when this paper was written. I think these days we can do the same thing with very complex, with higher dimensional games, but in those days, I think more than a decade back, we could not really use a lot of computation. So that's why you might see that these are very pixelated. Plus, these games go through some sort of post processing as well. There are, yeah, these are the visual inputs that they are talking about. Yes, these are the key concepts that that this particular paper comes up with. Also, there is this one loss function that they are mentioning, which let's dig deeper into it. All right. So look over here. This is basically the optimal action value function, or the Q function. This is what we often try to approximate at any given time in reinforcement learning. So the goal is to approximate the optimal action value function, that's q star, which represents the expected cumulative reward for taking action A in state S and following the optimal policy afterwards. So it it just shows you the probability of taking action A at any given state S. Fine. So instead of calculating this action value function for each state action pair individually, which would be computationally impractical because imagine that you are playing something like Breakout. This game is always going to start at some random point. Of course, those rainbow strips will might stay the same if we do not jumble them to make it more difficult. But imagine that even if they are staying same, this ball might start somewhere else. The ball might start moving in some random direction. So every time our agent tries to play this game, he is going to come across a very new, a very different state that he might never have encountered before, which will become a problem if you just keep on storing that, okay, in this particular state will do this action. That tabular method will not work in this case. So instead of calculating these AV action value functions for each state action pair individually, the researchers use neural networks as this function approximators. These neural networks are basically called as Q networks. I forgot if they have mentioned this exact term in this paper or not. But yes, these are helpful for action value approximation at any given state. Fine. I think they have. I think they have. Just look into it. Fine. So these Q networks take S as an input, that this particular state as an input, and outputs the predicted Q values for all possible actions. Fine. So, okay, let's look back to the example. Fine. We have almost lost this game, so let's not talk about this, but let's look into this one, this Pong game. Imagine that this is the agent that's learning, the green one. So what this green one do is, what action should this green one take? Think about it, right? So this is one particular state. This one snapshot that you see right now on the screen is the state that our neural network or Q network will take in as an input. And what will it output? It will output the maximum probability of going upwards in the up direction, and there will still be some probability of going downwards or staying at the same place, fine, but the maximum probability would be of going upwards, because that's how this Q network is trained, right? So I hope you get an idea of what the input and output will be of any particular given state or this game. Fine. Okay, the state is not just one snapshot, so that's another trick that they are using. The state is a collection of four consecutive snapshots. Why four? Well, why not, why four and why not just one? Because having this snapshot is not giving you complete information of in which direction this ball is moving in. If you don't even know which way is it going, is it going left or right from this one snapshot, right? Like this is the snapshot of this ball, who can tell me that it's going on the right direction or left direction? No one can. You need some sequence of these snapshots just to give you an idea that, okay, yeah, it might move in the right direction. If it's going in the right direction, the green pedal must move. If it's going in the left direction, the orange pedal must move, things like that. So that's why it's using four frames as state. The weights of this network are represented as theta, um, over here. So that theta, yeah, function of its weights theta as the Q network. Fine. I hope you understand the setting of it. Now, this Q network is trained by minimizing a loss function that quantifies an error between the predicted Q values and the target Q values. The loss function is given over here. So this is basically the loss function that is helping us achieve our goal. And after getting this loss function, the target Q values, Y are is calculated using the Bellman's equation. So, if you do not know what Bellman's equation is, that's one of the most important equations in reinforcement learning. And I believe that any kind of problem can be converted into a Bellman equation of some or the other sort. And in reinforcement learning, you should always look into a Bellman equation, which gives you an idea of what are the inputs and outputs of a problem, and how exactly is this problem being solved using what loss functions. So these are the different questions that arise when we talk about Bellman equation. But these questions answer a lot of different concepts that are very important while reviewing a paper as well. So always look into that. Fine. So now we know the loss function. Now we know what is the target q value yi that we are trying to optimize for. The loss function is minimized using something known as stochastic gradient descent. It is mentioned over here. And this actually updates the weights of Q networks based on calculated gradient from randomly sampled some mini batch of transitions, that is this past experience that we called experience replay before. This experiences are stored in the replay memory. Well, going back to experience replay is used to break this correlation between samples and reduce the variance of updates and smoothen the learning distribution, which helps avoid divergence of parameters. Again, reinforcement learning also faces the issues of divergence and lack of those proofs. Yes, there are proofs available to some extent. Not exactly sure on which algorithms though, but we assume that in practical implementation, if things work, then you can use them. And I just read it in one of the books. I'll probably link that in the description, but not exactly sure if all the proofs exist or not. After introduction of deep reinforcement learning, I have not seen a lot of people proving conversions. So probably. Again, one more thing. This algorithm uses epsilon greedy policy for exploration. That's what I think we already discussed. Where the probability 1 minus epsilon, it selects the action with the highest predicted q value, that is it goes greedy for like 1 minus epsilon times, and it goes quite stochastically or random actions with probability epsilon. So these are the two things: greedy strategy with epsilon. Yes. Exact same thing, not very new. If you have already learned about reinforcement learning, you already know about this. If you do not know reinforcement learning and you want me to make some good video around it, please let me know in the comments and I'll definitely look into it. So this allows for exploration into different state space. Yeah, I guess that's all about this particular paper. Mm, one very important thing that we are missing is what exactly are the results. By the way, I'll highly encourage you all to go through the experiments section yourself. Again, this paper is one of the most important papers that I love a lot. I think it could be my personal opinion, but it's an amazing paper. It teaches you a lot of things. For example, you see the average reward on breakout, it keeps on increasing. On Sequest also increases. There is some randomness there, but you see it's not always zero, or it's not close to zero always. It goes really high. Average reward per episode. Average Q values on breakout also increase. So these are the average Q values which you can see. It means that the algorithm is learning. It's not a bluff. It's not basically some random thing. Another great part about this paper is the way it is showing how the algorithm is thinking. So this is a ship that we are playing right now. Fine, makes sense. These are different enemies. These green ones, 1, 2, and 3. Now, okay, just a second. I might have to see which frame number is it. Yeah, it's frame number A. Yeah. So these are basically three frames out of past 30 frames. Frame number A, B, and C. Fine. So let's look into frame A. Let's not look into the graph just yet, even though you have seen it. But let's think of it from the human's perspective first. If you're playing this game, what you would do? Well, if I were playing the game, I would actually go downwards and then shoot the near ones, probably because I want to shoot all three of them. But imagine if I were not that smart. If I were someone, if I were just someone who is starting out to playing this game, I would try to shoot the enemy right in front of me, and just like this, the enemy is right in front of me, and I killed him. And you'll see that I increased my score from 40 to 60. Fine, these are the three frames, like just one thing that I did into three frames. Now let's look how it impacts our Q values. Well, initially, when the algorithm saw that there is this enemy coming in front of it, it spiked up. Now it knows that if there is something in front of it, it can definitely kill it. Fine. It is trying to predict that if it goes into shooting a bullet towards that enemy, will that enemy will that enemy be killed or not? And again, this game is pretty simple because the enemies are only moving in the right direction. It's just moving towards the ship. So nothing very interesting or nothing very difficult. But as from the computer's perspective, now the computer knows that okay, there is something that it can kill in front of it and gain some reward. So you'll see this Q values or the Q value has spiked up and it has shot up. Now, in the B scenario, when you are shooting the bullet and you have already shot a bullet right in this one frame, next in the exact next frame, the enemy is going to get killed. Simple as that. So in that case, we are in the B scenario, B frame, and you will see over here the Q values peaked. So that was the highest point of Q values. And after that, in the last scenario, in this one state, when there is no enemy in front of it, the Q values go completely down. Make sense? Because there is nothing to kill in front of it. There is literally no way it can gain reward by just shooting his bullets. Fine. So this is how reinforcement learning tries. So this is how agents try to learn using RL, and this is basically a visual representation of what Q values look like. Fine. Okay. So how well did this AI actually perform? Well, it learned to play I think seven different games like these ones. Right. So one, two, three. Yeah, these are seven different games that it learned to play, and in many cases it outperformed previous AI systems designed specifically for those games. Well, it even beat expert human players in playing games like I think Breakout, Uduro. I'm not sure how to pronounce that, but Uduro and Pong. These are the three games where it even beat the human. But in I think only in one of these games it could not outperform an expert AI algorithm previously. Hmm, I cannot really find that out. Yeah, this one it is. This one. I should mark this. Fine. So over here, Invaders, Space Invaders is the game in which it could not beat HNet best. Little sad for this algorithm, but I think that's just fine. The thing is, it's not perfect. The AI struggles over the games that require long-term planning and strategy, like those where you have to think many steps ahead. Still, the fact that it could learn directly from raw pixels data just by looking at the screen, that's actually very huge because we have a lot of information in pixels right around us. We have got videos, we have got images, we have got all sorts of data surrounding images and pixels, which can be used to train an algorithm or deep learning or reinforcement learning models. This paper actually opens up that possibility. Before this, yes, people tried to do it, but their algorithms did not perform really well. This is the one which completely started, or I would say, this paper actually began a new way of thinking around how we can use experience replay to our advantage. So that's it for this one paper. Let me know if you have any doubts or questions in the comment box, and I'll definitely try to come up with several tutorials around reinforcement learning if they're any helpful. But that's it for this one. Thank you so much.